Okay, for quiz 9, question 1 asks you which of the following is the strongest reduction agent? A. Aluminum. B. Copper. C. Zinc. D. Lead. So from the standard potential, we provide the air body table, right? The reduction potential, more negative, is stronger reducing agent. Okay, not a reducing, it should be reducing agent. Reducing agent. More negative potential, stronger reducing agent is the left side of that half reaction. But for me, I even don't need to use this table because stronger reducing agent, this means easier to lose electron. In other words, it's a more active metal, right? Of course, group 1A, lithium from group 1A is a most active metal. So this should be the strongest reducing agent. Choose D. And the second question asks you which one is the strongest oxidizing agent. A. Chlorine. B. Oxygen. C. Bromine. D. iodine. Or non-metals, right? Oxidizing agent, either non-metal or metal ion, right? Reducing agent normally is metal. Oxidizing agent, non-metal or metal ion. They gain electron. Which one has strongest tendency to gain electron? Then that is strongest oxidizing agent. So group 7, 8 are the strongest agent because they have strongest tendency to gain electron. But we have 3 from group 7, 8. Right? Chlorine, bromine, iodine. From group 7, 8, strongest oxidizing agent is the fluorine, the first one. Then move down becomes weaker and weaker. But anyway, group 7, 8, all very strong. Right? Within the group 7, 8, fluorine stronger than chlorine, chlorine stronger than bromine, bromine stronger than iodine, right? Since fluorine not listed here, so chlorine is the strongest. So A, chlorine is the strongest. Question 3, in an electrolytic cell, electrical energy is converted into chemical energy. A, true. B, false. So what you want? In carbonic cell, we use spontaneous chemical reaction to generate electricity. While in electrolytic cell, use electrical energy to force a non-spontaneous chemical reaction to occur. So without electric current, that chemical reaction will not happen because it's non-spontaneous. But if we connect it to electrical power, then electric current will force that reaction happen. So chemical reaction happened, then convert into chemical energy. Right? This is true. Again, galvanic cell use spontaneous chemical reaction, convert chemical energy into electrical energy. Now use electrical energy force a chemical reaction happen. So electrical energy converts into chemical energy. That is true. Then question 4. What is the cell potential for the reaction shown below at 298 K? Copper concentration 0.5 molar, or zinc iron concentration 0.1 molar. As you calculate these whole reactions potential difference or cell potential. Zinc metal react with copper iron produce zinc iron, and copper iron be reduced to copper metal. The standard potential difference for this reaction is 1.1 volt. So this E0 actually already is a potential difference between zinc iron zinc and copper iron copper. These two half reaction. Right. So for the whole reaction, this is the potential difference between the two half reactions. So this 0 means the standard condition. No, not at the standard condition. Standard condition means every iron's concentration is 1. No concentration is 0.5 for copper iron and 0.1 for zinc iron. So this potential difference between two half cell is the Nernst equation. So at 98 K, F over RT together will be 0.05916. Actually, to convert a natural log to 10 base log. So if temperature is at 25 degrees Celsius or 298 K, so Faraday constant over R as a gas constant and the temperature in K, so these three give me 0.05916. Then log part is product, right side, product in top. Exponent, so coefficient is 1. Reactant in bottom. Exponent also 1. And this is solid, don't need to be there because solid concentration always 1, right? So this we call Nernst equation. Again, this 0.05916 come from temperature at 25 degrees Celsius. Used to be, this is a Faraday constant, NFE, right? So over RT, natural log, right? Natural log product iron concentration raised to some power. Depends on the coefficient in the balance equation. And the reactant concentration raised to some power depends on the coefficient in the balance equation. Okay. So natural log converted to 10 base log unit times 2.303. together with Faraday constant and gas constant. The 25 degrees Celsius is 298 K. So this together is 0.05916. Okay. So this is a Nernst equation. All right. Now E0 is a non-body. This is standard potential difference. It's 1.1 minus 0.05916. 2 comes from the number of electron transfer from copper 2, positive 2 becomes copper iron, copper metal is 0. So 2 electron transfer. This is 2 times log zinc iron concentration is 0.1. Copper iron concentration is 0.5. So use your calculator. So 0.1 over 0.5 is 0.2. Log 0.2. Use your calculator. Then times this divided by 2. Then subtract this from 1.1. You get a 1.12 volts. Okay. Sure equation like this. Sure you need to write the initial equation first. Then plug into number. Then give answer. Each step will worth some point. So do not skip. If you skipped, and if your answer is wrong, then you don't have partial credit. Okay. Then question 5. Use the standard reduction potential from the table provided. Calculate the equilibrium constant K for the following reaction at 25 degrees Celsius. So the following reaction took place at 25 degrees Celsius. Serum 4 react with chloride iron. Produce serum 3. And the chloride iron becomes chlorine gas. So here we need to find the standard potential difference between Cerical 4 and Cerical 3 and chlorine chloride. Right, this is 2 half potential. The potential difference will be Cerical 4, Cerical 3 minus standard potential of chlorine chloride. The question is why the potential difference is Cerical 4, Cerical 3 minus chlorine chloride standard potential, not chlorine chloride standard potential minus Cerical 4, Cerical 3 pair. The easiest way to judge which one minus which one is because this standard potential or reduction potential means always based on the reduction reaction. Reduction reaction is gain electron. For this case, Cerical 4 gain 1 electron becomes Cerical 3. This is the actual reduction. That's why put this first. The other one, chloride becomes chlorine. This is a lose electron. This is oxidation. This is the opposite. That's why it's negative. So Cerical 4 to Cerical 3, this is actual reduction. Then minus chloride becomes chlorine. This is oxidation. This is opposite. This minus it. Okay. This is the easiest way to judge which one minus which one. Okay. So from the table provided, Cerical 4, Cerical 3 pair is 1.61, and the chlorine chloride pair is 1.36. The difference is 0.25. If you use this minus this, then your E0 becomes negative 0.25. Then your result will be wrong. Okay. Again, because our reaction actually is Silica 4 becomes Silica 3, so this is a reduction. The other one, chloride becomes chlorine, is oxidation, so you need to minus it. Then E0 link with equilibrium constant K is this at 25 degrees Celsius, 0.05916 divided by 2 times not log K. This is similar as the one in question 4 we just explained, right? So now it's E0 equal to 0.05916 over 2 times log K. This 0.0596 comes from Faraday constant F divided by RT. T at 25 degrees Celsius convert to Kelvin's 298 K. So Faraday constant divided by R, gas constant divided by 298 K. You get this number. 2 is because 2 electron. So Silica 4 to Silica 3 is 1 electron, but you have coefficient of 2 there. So 2 times 1 is 2. This is log K is equilibrium constant. From here, we can get this K will be equal to 2 times E divided by 0.05916. Then exponent 2E0 divided by 0.05916 is the power. Right. So both sides times 2, then both sides divided by 0.0596. Then take the on the log. So that's 10 base. That's why it's 10 to this power. And now just plug in the number. E0 is 0.25. So this gives us answer is 2.79 times 10 to the 8 to the power. Or textbook have another equation is instead of natural log, instead of 10 base log, we keep natural log. If you use natural log, then this number will be 0.0257 divided by 2 times the natural log. Yeah, because natural log, the 10 base log times 2.303. If you times 2.303 by 0.0257, you get this. From here, you get is E to the 2E0 over 0.0257. E to the 2 times 0.25 over 0.0257. The result is the same. You can either use the 10 base exponent or E natural log. Final answer will be same. Question 6. Again, use the standard reduction potentials from the table provided. Also, you calculate the standard Gibbs energy change for the reaction and equilibrium constant K for this reaction at 25 degrees Celsius. So this reaction again at 25 degrees Celsius. The reaction is magnesium metal react with PBr, produce magnesium iron and PB metal. So also you calculate standard Gibbs energy change and equilibrium constant from the standard potential. The standard potential we can find from the table provided. So first of all, find the standard potential and calculate the potential difference between the two powers here. So potential difference is 2 half cell potential difference. Again, the similar question is why is standard potential of lead R minus lead R lead minus standard potential of magnesium R magnesium, not magnesium R standard potential minus lead R standard potential. Because this reaction tells us lead R reduced to lead. This is the actual reaction direction. This is a reduction reaction. The other one is magnesium metal. Lose electron become magnesium ion. So this is the opposite of reduction. So it should be minus. Okay. Use my way. You can easily judge which one minus which one. You never make a mistake. So lead ion reduced to lead metal. So this is first minus magnesium ion magnesium. This is opposite. So minus it. So from the table provided, lead iron lead standard potential is negative 0.13. Magnesium iron magnesium metal negative 2.37. The result is 2.24 volts. Then the standard reaction gives the energy change of the reaction is delta G 0 equal to negative N times F times A0. N is the number of electron transfers. So clearly, for this balanced equation, 2 electron transfer lead 2 become lead metal. This is 0, right? 2 electron transfer. The magnesium 0 becomes the magnesium 2, also 2 electron transfer. So N is 2. Negative NF E0. F is a Faraday constant. Here, provided you this number here. Faraday constant 9.647 times 10 to the 4th power coulomb per mole. And E0 we just calculated 2.24 volts. So use your calculator, you can easily get this is 4.32 times 10 to the 5th power. Coulomb times volt. This is joule. Joule per mole. Okay. For energy change gives energy, stirs energy, right? So unit is joule. Even if you don't know Coulomb times volt will be joule. But from the gives energy change, gives energy is energy. Energy unit is joule, right? Still there. And this delta G link with equilibrium constant by this equation. Right, delta G0 equal to negative RT times natural log K. Then K equal to E to the negative delta G over RT. Right, both sides divided by negative RT. Then E based, so E to this power. Then plug in the number. Delta G itself is negative 4.32 times 10 to the 5th power joule per mole. Be careful, negative delta G. Delta G itself is negative value. R is a gas constant. Here also tells you it's 80.314 joule per mole per K. Then T here tells us temperature at 25 degrees Celsius, so convert it to Kelvin. Plus 273.15. K cancel this per K. Joule cancel this per joule. So this exponent part is a pure number, which is 174.4. The result is 5.51 times 10 to the 75th power. This is the equilibrium constant for this reaction. So equilibrium constant link with delta G. Okay. And the delta G link with standard potential. So standard potential, delta G, and equilibrium constant, these 3 properties are linked with each other. Okay. That's it. I wish everybody review your quiz 9 carefully. to prepare the final exam. Final exam for Chem 2, we use ACS standard final exam, include the sum from Chem 1 and all we learned in this chapter for Chem 2. Bring a schedule to class.